So we've looked at a lot of irrational numbers that are generated from roots. Now these are called algebraic irrationals. There are lots of other irrational numbers as well, and some of them are quite interesting. One of them is phi. Phi is called the golden ratio, and phi shows up in a lot of different ways. So phi, and there's two different phi's, big phi and little phi. So big phi is 1 plus root 5 divided by 2. This is approximately, this value is approximately equal to 1.618 dot 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 dot. Okay, and there's also another number called little phi, and this number is the exact same number without the 1. And I'll explain the relationship to you in a second. So the golden rectangle, the phi shows up in the golden rectangle, and it is the ratio of one side to the other side. So the long side is going to be 1.618 dot 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 dot, and that other side is equal to 1. Now what's interesting about phi is that if we slice it up, if we divide it up into a square, this square here, which the side lengths are 1, we're going to have leftover part here 0.6. Let me just clean that up a bit. I'm going to zoom in. This will be 0.618 dot 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 dot, and that ratio to 1 happens to be the exact same proportion as 1 to 1.618. And what ends up happening then is we can regenerate that same rectangle every time we slice it up. And you may have seen this spiral drawn into this diagram, and this is called the conch spiral, and it is related to the golden ratio. So the golden ratio also shows up in the golden triangle. Okay, so the golden triangle can be by making a regular hexagon, and the length of the one side to the length of the equilateral triangle made inside, that is a 1 to 1.618 ratio. And that is a golden ratio. So here I've drawn it as 0.618 to 1, but that ratio is the same as 1.618 dot 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 to 1. These ratios are exactly the same. And so what ends up happening is anytime you have a golden ratio, it seems to kind of regenerate itself. So if I can connect these lines here, and when I have this pentagon, I can draw a pentagram inside, and inside that pentagram, draw a little bit nicer here, inside that pentagram we regenerate a pentagon. And we can keep on doing that indefinitely, like we can do with the golden rectangle. The other thing is, if we take the golden triangle and we just take that piece there, this new triangle formed is in the same proportion. It's a 72, 72, 36 degree triangle. It is forming another golden triangle, and with the same proportions, the same properties, and again, it will regenerate itself. So the golden ratio seems to have this special property of regeneration. So there are other numbers, irrational numbers that if we tried to find them, we would never be able to find them. But these ones always just pop up everywhere. These are not algebraic irrationals. They're not formed by any roots. These ones just kind of show up. And these ones are pi and e. Pi and e is also called Euler's number. And these ones just show up. If we tried looking for these two numbers, we would never be able to find them. However, they just appear everywhere in math. E and pi just show up everywhere. For some reason, they just show up all the time, which means that they have something to do with all the world around us, and they're integral to the world around us. So we don't know exactly what they do, but they are important in that they are everywhere. And if we actually, they're infinite number of numbers like pi and e, but those ones don't show up, and we can't find them even if we wanted to. And same with pi and e. If we wanted to find these, we can never find these, but these ones come to us. So there's something special about these numbers. I'd also encourage you to watch this video on pi. So that tells you a little bit more about pi.